Welcome to the sixth episode of our series, The Mother Earth. In this episode, we will look at the asteroid belt that exists in the space between 2.1 to 3.3 AU, that is, in the gap between the orbits of Mars and Jupiter in the solar system. In episode 1, we learned already that the Earth's distance from the Sun is 1 AU, that is 150 million kilometers. You can now imagine how distant is the asteroid belt, isn't it? The total mass of the asteroid belt is very small, just 3 to 4% of our moon's mass or lunar mass, or about 1,000th that of the Earth. Despite that, you will realize how important it is to know about what exists in the asteroid belt. The outer boundary of this belt is about 500 million kilometers from the Sun. It is also referred to as the frost line, since beyond this distance, all volatile substances in the solar system have condensed to ices, forming the cores of the outer gaseous planets. The inquisitiveness of the 18th century astronomers about the occupants of this space got the most valuable input about 2 centuries ago. In 1801, when the largest asteroid named Ceres, about 946 kilometers in diameter, was spotted by the Italian astronomer Giuseppe Piazzi. Compared to the Earth's diameter of 12,743 kilometers, Ceres is very small, isn't it? The planet Mars also, beyond which the asteroids exist, is rather large, diameter 6,794 kilometers, compared to the Ceres. Besides Ceres, 3 more large asteroids named Vesta with diameter 525 kilometers, Pallas 512 kilometers, and Hygiea, diameter 434 kilometers, have been discovered in the later decades. Their characteristics, like the size, axial angle, periods around the Sun, density, spectral compositions of their crusts, the albedo, the inclination of their orbits with the ecliptic, have all been recorded, deploying more sophisticated technology in recent years. Detailed information has been gathered by spacecraft missions like the Dawn mission of NASA, carried out from 2007 to 2018, which traveled through the asteroid belt. This episode, therefore, focuses first on the comparative characteristics of these 4 asteroids, referred to also as the protoplanets. It correlates their accretion history and compositions with the composition of the meteorites, about which we learnt in the 5th episode. These four large asteroids together accreted almost half the mass of the entire asteroid belt. These protoplanets, or the planetoids, acquired near spherical shapes because of their own internal gravity. Asteroids of different shapes and sizes, some semi-spherical, also exist, many with short diameters or lengths of only a kilometer. They are referred to as the planetesimals. The still smaller ones are known as meteoroids. In episode 5, we referred to the glowing meteors traveling through the Earth's atmosphere and to the meteorites which impacted its crust. When the meteoroids get dislodged from their orbits, they get pulled by the gravitational forces of the inner planets. Some of them reach the Earth. All these planetary bodies orbit the Sun, but their orbits have different inclinations. The gravitational pulls of both Jupiter on the outer side and Mars on the inner side of the asteroid belt keeps these planetary bodies apart. Let us view first the large asteroids, then the planetesimals, and then the meteoroids. Cirrus, the largest asteroid, has a density of 2.8 grams per cc, and it orbits at an average distance of 2.8 AU from the Sun, revolving once in 4.6 years around the Sun. Since it has small axial tilt of only 4 degrees, it is not expected to have any permanently shadowed craters which may contain primitive water ice. The spectral composition of its crust points to the presence of deposits of sulfate and carbonate salts of sodium, potassium, and calcium, along with hydrous silicates like the clay minerals containing potassium, aluminum, silicon, and the hydroxyl molecules, together with water ice and carbonaceous matter. It is inferred that occasional volcanic eruptions on it expelled the brines from its 100-kilometer thick mantle, which is in fluid state, and have deposited these salts. The eruptions have been caused by collisions and impacts with other asteroids, small and big, during its earlier history. The numerous craters visible on its surface reveal that the collisions continued after its crust formed. Cirrus formed a solid core constituted of silicates prior to the formation of its crust. The core is silicate-rich, not metallic. Pallas is marginally denser than Cirrus, with a density of 3.0 grams per cc. It revolves with a period of 4.62 years at an average distance of 2.77 AU from the Sun. The orbits of Cirrus and Pallas are not far from each other, but their inclinations to the ecliptic differ. About 10 degrees for Cirrus and about 35 degrees for Pallas. The orbit of Pallas is more elliptical because of which it comes closer to the Sun than Ceres. The axial tilt of Pallas is far too oblique. It is 84 degrees. The crust of Pallas has a different composition than that of Ceres, dominated with silicate rocks containing tiny crystals of Fe-rich olivine and pyroxene as the mineral constituents. We refer to such small spherical chondrules of pyroxenes and olivine in most chondrites in episode 5, didn't we? The chondrules pointed to the internal melting and crystallization involved in the formation of chondrites. Pallas has a hydrated mantle beneath, perhaps partly molten, with low viscosity and an anhydrous silicate-rich core. Vesta is occasionally visible without using a telescope. It has a higher albedo compared to the other three large asteroids. What is albedo? It is the proportion of incident solar light that is reflected by any planetary surface. Though Vesta has an axial tilt of 29 degrees, the albedo revealed its rocky surface. It is distinctly different from other distant asteroids, which are partly or completely covered by carbonaceous matter, basalts, ice, and salts. Vesta has a period of 3.63 years and has the highest density of 3.42 grams per cc, which is quite comparable to that of Mars, that is 3.93 grams per cc. Vesta orbits closer to the Sun at a distance of 2.36 AU, and being proximal to Mars, its overall composition resembles that of Mars. Vesta has a molten Fe-Ni-rich core, which perhaps accreted rapidly in the first 10 million years of the solar system. It has less viscous mantle, constituted mainly of olivine pyroxene minerals, and a basaltic crust of about 30 to 40 kilometers thickness. The crust of Mars is also containing hydrated silicates. Vesta has a highly cratered crust, which provides evidence for its collision impact history even after its crust was formed. The craters on its surface have been intact since the impacts and are clearly detected because of the absence of any atmosphere. Similar is the cause why the highly cratered lunar surface or the surface of Mercury are clearly visible. Its average surface temperature varies between minus 188 degrees centigrade and minus 18 degrees centigrade, decreasing towards its poles, similar to that of the Earth's surface. But since there is no atmosphere, the surface temperature could not hold any water ice on its surface. The large asteroid Hygiea, with 434 kilometers diameter, at a distance of 3.14 AU, proximal to Jupiter, is almost at the frost line. Its orbital period of 5.57 years makes it the slowest asteroid revolving around the Sun. The slow speed is due to the strong gravitational pull of the giant planet Jupiter. Despite the proximity to the gaseous giant, it has a solid crust and a bulk density of 2 grams per cc. But because of its axial tilt of 60 degrees, the surface temperature varies too much from minus 437 degrees centigrade to minus 26 degrees centigrade. Unlike the surfaces of other 3 asteroids, Hygiea shows no impact craters. Not because it didn't suffer any impacts, but perhaps it got totally shattered in the initial incessant collisions. But its fragmentary debris got recoalesced because of the gravitational pull of Jupiter. The recoalesced Hygiea does not reveal any evidence of internal melting and differentiation. Its composition is akin to that of carbonaceous chondrites, which form a small group of 4% amongst the chondrites. That is inferred as the most primitive composition in the solar system. Amongst the planetesimals and meteoroids, those orbiting closer to Vesta are the most differentiated, some metallic and some rocky, while those orbiting closer to Hygiea should have the composition similar to the carbonaceous chondrites. The information enriched our understanding about not only the iron meteorites, chondrites and achondrites, but also about the carbonaceous chondrites. We have learnt in this episode that most fragmentary planetary bodies in the asteroid belt represent the leftover building blocks of the protoplanetary nebulae in the solar system. They have a differentiated composition varying from metal-rich to silicate-rich and even carbonaceous. Cirrus, Vesta and Pallas distinctly reveal the impact craters which have triggered volcanic eruptions. But even prior to the formation of their crust, there is evidence that the asteroids underwent internal melting and differentiation of matter, separating their cores from their mantles. That is revealed by the difference in the composition of their crust and their cores. That's what we can infer, isn't it? In the next episode, we will look into how this information on the asteroids, planetesimals, and the meteoroids enabled us to trace back the 4 billion years history of the pre-planetary melting and gravity separation in the nebulae of the terrestrial planets. Thank you.